In the name of Almighty God, I'm Mahsa Sankoshi, and today I want to talk about a weak gravitational lensing, the bullet cluster, and cosmic shear. Today, one of the most striking evidences for the presence of dark matter on the length of the scales of the galaxy's clusters comes from the observation of a pair of colliding clusters known as the bullet cluster, located 3.7 gigayears away, with a catalog name 1E0657 558 or 1E0657 56, and first observed in detail in 2006 as well as from similar systems. Most of the baryonic mass in the bullet cluster is in the form of hot gas whose distribution can be traced through its X-ray emissions. The distribution of the total mass, visible and dark, was independently measured through weak lensing. The special feature of the bullet cluster system is that the visible matter and dark matter are specially separated. See the figure 1.3 for more explanation. The interpretation is the following. In the past, each of the two clusters of galaxy was an ordinary system with the visible matter and dark matter mixed together. The two objects collide 150 million years ago. Visible matter interacts significantly with itself, so that the hot gas from the two clusters experience a collision shock wave. Dark matter, on the other hand, experiences negligible collisions with itself and with normal matter, such that the dark matter clouds of the two systems simply pass through each other. This led to the present separation of the visible and dark matter components apparent in Figure 1.3. After the observation of the bullet cluster, many similar systems have been studied. Harvin and his colleagues in 2015 in their reference 13 reports that the results on 72 of them and conclude that the existence of dark matter can be established with a significance of more than 7 sigma. This kind of the observations puts severe strain on alternative interpretations which dark matter is replaced by a modification of gravity. Such modifications cannot get spatially separated from normal matter unless they too introduce something that effectively behaves as dark matter, so that the anomalous lensing signal would follow the distribution of the visible matter, as we will discuss in more details in chapter 11. The bullet cluster and similar systems also provide information about the particle physics properties of dark matter. The fact that the dark matter halos did not slow down compared to the collision less trajectories implies an upper bound phi is equal to sigma n r cl is less than almost from the 1 on the probability feed that a dark matter particle scatters with another dark matter particle on the typical scales of the system. Here, sigma is the dark matter self interaction cross section, n is the dark matter number density, and RSCL is the size of the cluster. In the specific case of the bullet cluster, data indicate RCL is almost equal to 150 kpc and rho is equal to 0. Giga electron volts divided by per cubic centimeter. Observation provide information on the dark matter density. Rho is equal to mn and not directly on the dark matter number density. So one obtains a bound on sigma per m, where m is the dark matter mass, and the different studies find slightly different values in the ballpark of which in roughly a factor of 2. Sigma divided by m is less than 1 multiplied by square centimeter divided by g is equal to 1.8. mb divided by g EV is equal to 4580 divided by GeV to the power of t. When assuming point interactions for comparison, 50 MP is the typical uh, chromium dynamic cross section, for example, pp scattering. The bounding equation 1.5 is that satisfy if dark matter is made of the particle somewhat heavier than protons and or somewhat less strongly interacting than protons. The dark matter cross-section is similarly bound by the astrophysics and cosmology to be roughly smaller than quantum chromium dynamic size at m is almost equal to 1 gigaelectron volt, also a number of other much more stringent constraints apply. See the full discussion in the section 5.1.2. Cosmic shear at length scales, but somewhat intermediate between the galactic cluster and the cosmic scales. The detection of cosmic shear also provides evidence for dark matter. Cosmic shear refers to the deflection of light from very distant galaxies by the gravitational attraction due to the foreground mass concentration. These are not in the form of the dark matter halos of galaxies or clusters, as was the case for the galaxy-galaxy lensing and for the case of cluster collisions discussed above, but rather in the form of much larger and diffuse structures such as vast filaments and loose clumps. The measurements are performed statistically on a very large number, millions of distant galaxies, using multi-wave length surveys, which have to be very deep, detecting very distant galaxies, and very wide, exploring large portions of the sky. The shapes of the distant galaxies are distorted by the shear, changing the major to minor axis ratios by about 2%, which can be detected on a statistical basis. The observations determine omega dark matter is almost equal to 0.25. The importance of cosmic shear goes well beyond the mere additional evidence for the existence of dark matter. By reconstructing the matter distribution along the line of sight, one is effectively looking back at the formation history of the large dark matter structures that provide the scaffolding of the universe, which we discuss in the next section. A phenomenon along similar lines is the so-called CMB lensing, which involves searching for distortions of the CMB map caused by the foreground mass concentrations. In a way, this is the ultimate application of weak gravitational lensing as a tool to probe dark matter, since the CMB is the earliest observable light. It provides a unique opportunity to investigate extremely large dark matter structures at high redshifts. Z is greater than the 2, and CM lensing has been detected with the highest statistical significance, both in data from Planck as well as from other experiments. See, for example, the reference 18 for review and recent Planck results corroborating the evidence for dark matter. The effect of the lensing is to reshuffle the CMB perturbations. Notably, it smooths out the peaks at large L in the CMB power spectrum and affects the polarization of CMB photon, creating the so-called B modes out of E modes. In fact, from the perspective of someone interested in the primary CMB lensing, is a contaminant and has to be subtracted. For example, the CMB spectrum has to be delensed. Now I want to go through another subsections 1.3, Maxi the universe. The most convincing and precise evidence for the existence of dark matter comes nowadays from the largest scales possible, the entire observable universe. The basic point qualitatively is that the universe would not have acquired the appearance that we observe today if not for the role that dark matter played. Galaxies would not be distributed in the way they are, and the CMB temperature anisotropies would not the way they do. If it weren't for dark matter acts as the indispensable catalyst for the formation of structures. It brings the universe from the initial states characteristic by almost perfect smoothness with only tiny inhomogeneities to a state rich with structures at many different scales. It allows primordial inhomogeneities to grow, forming the galaxies observed today. As we will see later, ordinary matter cannot accomplish this task, essentially because of its coupling to the radiation. For the discussion below, we need some aspects of standard cosmological model quantitative description is given in Appendix C with Figure C.1 summarizing the evolution of the three main components of the universe quantitatively. The evolution of these three components can be briefly summarized as the first one is radiation. Radiation has density that scales at 1.1 per R to the power of 2 initially when the scales factor R was very small. Radiation, photons and neutrons dominated, and the universe was almost homogeneous and opaque to photons. The next is matter has a density that scales as 1 divided by r to the power of 3. At a later stage, the universe became matter dominated at the t is equal to 50 kiloyears when the universe was I equal to 1 divided by 3,400 smaller than today, and the transparent the recombination happened at the t is equal was equal to almost 380 kiloyears. For example, at R recombination is equal to 1 divided by 1100 when the universe cooled well blew the hydrogen binding energy so that the electrons and protons form neutral hydrogen. The next step is dark energy. So we had three stages. The first stage is that radiation and its scale is 1 divided by r to the power of 4, and the next one matter when it is most coolly, and 1 divided by r to the power of 3 it's a scales. After that we have a dark energy. Now scales factor is always equal to 1, so it is most of the universe because when denominator is larger from the and it makes the whole value lesser. So when we are talking about the dark energy and scale factor, you see that is all equal to 1, so it has been occupied most of the universe of a scale. Universe is dominated by a component whose density doesn't evolve with R, compatible with it being a cosmological constant or vacuum energy. In the remainder of this chapter, we work inside the framework of such a standard cosmological model. In the next subsections, we compute the formation of large-scale structures (LSS), while in subsection 1.3.3 we discuss the imprint of dark matter on the acoustic peaks of the CMB. These two props are illustrated in figure 1.5. Now I want to go through another section. Subsection is 1.3.1 large scale structure formation. Today the universe is very inhomogeneous on a scale smaller than its present horizon. Take for instance a result of galaxy surface such as the one shown in figure 1.5 top right, which corresponds to a three-dimensional map of a good fraction of a galaxy's in the observational universe. Already by eye one can resolve a variety of structures, lymph filaments, walls, voids, which appear at different scales. Other astronomical observations, such as the Lyman alpha forest, weak tensor measurements, cluster counts, and etc., concur in establishing the picture of a clumpy universe. Simulations and observations suggest that the voids or regions which density is equal to 10 times bigger than smaller than the average. They fill almost 77% of the volume while containing only 15% of the total mass. Walls occupy about 18% of the volume while containing about a quarter of the mass. Filaments provide the dominant contribution to the gravitational forces. They occupy about 6% of the volume and contain about half of the mass. Looms occupy a small sub-percent fraction of the volume and contain about 11% of the mass. Quantitatively, from all these measurements, one can extract the matter power spectrum pK plotted in the figure 1.5. Middle round right, it is defined via delta prime is equal to 2p to the power of 3 p delta to the power of t multiplied by minus prime, where delta is the Fourier transform of density contrast. Delta are defined more precisely in equation 1.12 below and denotes an average over co-orientations. The Dirac delta to the power of 3 multiplied by minus prime, not to be confused with the delta that denotes the perturbations, means that modes with different core is not equal to coupling happen to be statistically independent. This property can be understood from inflation, a theory that predicts average statistical properties encoded in PK. Since PK is a Fourier transform of the density self-correlation function, it conveniently expresses in Fourier space in homogeneity in matter distribution in physical space. A large or small value of pK means that there exist many few structures with the characteristic size 1 divided by k. The measurements shown in figure 1.5 middle right therefore show that the universe has some power on all scales to make the clumpiness of the universe even more apparent. Sometimes pK, which has units of length to the power of 3, is rescale into dimensionless variance. Delta to the power of 2k is equal to k to the power of 3pk divided by 2p to the power of 2. Small values of delta to the power of 2 corresponds to a small density contrast, while delta to the power of 2 is equal to 1, for instance, indicates an overdensity comparable to the average. A quick manipulation of the pK data in figure 1.5 middle right shows that indeed delta to the power of 2 rises to large values in the large core region. In other words, the data show that the universe exhibits large inhomogeneities on small scales for large core. In the standard cosmological model, the pyramidal inhomogeneities are generated from inflation with small amplitudes. Delta is almost equal to 10 to the power minus 5. This is confirmed from the near perfect smoothness observed in CMB, which essentially provides a photo of the photon content of the universe taken from when photons last scatter. So we reached the figure 1.5, which is illustrating the power spectrum of the CMB acoustic peak, middle row left. So middle row left here it says CMB acoustic peak is extracted from the map of the temperature on entropy top left. The matter power spectrum middle right is extracted from the extensive galaxy surveys top right as well as from other mapping probes. The same quantities in absence of dark matter are illustrated in the bottom row, and you will see that here we have actually CMB acoustic peaks here and CMB power spectrum in the and in the next one we have in x-axis wave number, and you see we have a bell shape that in five different methods, and in the y-axis we are studying about the current power spectrum, and the most current power spectrum is the 2 degrees of freedom galaxies here, and the next one is the black one cosmic microwave background, and the next one is the Lyman alpha forest. Chapter 1.3 is still we are in the universe. This poses a question: how could the tiny primordial inhomogeneities grow from such small amplitudes to the large contrast that we observe today? The answer, as anticipated above, is that the growth of the density perturbations is crucially driven by the presence of dark matter. In order to quantitatively understand how that happened, we need to sketch their evolution in the early universe. Let us consider a universe filled with generic matter fluid whose exact nature we leave for the moment unidentified. The main features of the evolution of density perturbations of such a medium can be understood by approximating the full general relativistic computation, which, with its Newtonian limit, this is a valid description of non-relativistic matter at length scales smaller than horizon. A non-relativistic fluid is fully characterized by its density, rho RT, by its velocity field, rho nu RT, and by the equation of state for the pressure phi. Its gravitational interactions are described by the Newton potential phi. These quantities are governed by the evolution Euler equation, and we have a derivative of the density based on the time plus delta rho nu is equal to 0, and it's for continuity. And when the Newton law or acceleration is equal to force divided by mass, we have a derivative of mu based on the time plus nu delta nu is equal to minus delta phi divided by rho minus delta phi. And then we have a Poisson delta to the power of 2. Phi is equal to 4p gp, which form a system of nonlinear differential equations for a quasi-homogeneous universe. It is possible to gain useful analytic information by expanding the above quantities as the first order perturbations to the zero order homogeneous background. Rho is equal to rho 0 t plus rho 1 xt, and we have a phi. For example, uh, phi 0 plus phi 1, and nu is 0 plus nu 1, and phi is or capital phi is equal to capital Phi 0 plus Phi 1. We first consider the case of a static universe, no expansion, equations 1.6, reduced to a set of coupled equations for the perturbations. You see that we have a static universe formulation 1.8, the derivative of density based on time plus rho 0 delta nu 1 is equal to 0, and derivative nu 1 based on the time plus nu s to the power of 2 divided by rho 0 multiplied by delta rho 1 plus delta phi 1 is equal to 0, delta to the power of 2 phi 1 is equal to 4pg p rho 1, where we define the quantity nu s to the power of 2 is equal to delta f, or derivative, partial derivative of the phi based on the density is equal to phi 1 divided by rho 1, which is interpreted as the sound speed in the fluid, as we will see in a moment. By acting with the partial derivation based on the time of the first equation and performing appropriate substitutions in each using the second and third equations, one arrives at one evolution equation for the density perturbation rho 1. For example, the genes equations, we have a second derivative of rho 1 based on the time minus nu s to the power of 2 delta to the power of 2 rho 1 is equal to 4pg rho 0 rho 1. Ignoring gravity, for example, setting g is equal to 0, the solution are density waves, for example, sound that travel at a speed nu s, including gravity. The full equation expresses the competition between a pressure term on the left hand side and a collapse term on the right hand side. The gene lengths, the lambda j is equal to square root nu s to the power of 2 divided by 4 pg. Rho 0 discriminates which terms is dominant. Perturbations on larger scales, lambda is greater than lambda j, collapse and grow in time, while perturbations on a small scale, lambda is less than lambda j, are supported by pressure. The growth with time of collapse modes is exponential. Rho 1 is almost equal to e to the power of square root 4 p rho 0 t, as one can easily check by solving the differential equation 1.9 for nu 0 tends to 0. This is the gene instability that, when applied to normal matter, explains how gas clouds collapse to form compact bodies, for example stars. The universe meaning of the gene scales is that a cloud of gas collapses when it is so big that is hydrostatic pressure, which prevents the collapse on time scales. Tau pressure is almost equal to lambda j divided by nu s, is too slow to stop the gravitational attraction, which clamps it on a time scale. Tau gravity is equal to g rho 0 to the power of minus 1 divided by 2. One can also define the gene mass as mj is equal to 4p rho lambda j to the power of 3 divided by 3. For example, as the mass close in a sphere of reduced lambda j, perturbations with mass m is greater than mj are gene stable, unstable, and collapse. We move next to the case of an expanding universe, solving the zero order quantities, describing the smooth background gives the Hubble expansion. As that we have in the equation 1.10, rho 0 t is equal to rho 0 t c divided by r to the power 3. No 0 is equal to hr, and delta f 0 is equal to 4 p g p rho 0 divided by 3 r. So, for T, the usual scale factor of the universe has been left with an unspecified time dependence. Solving equations 1.6 would determine the expansion RT of the matter-dominated universe. In general, extra components, radiation, and the cosmological constant contribute to the expansion, and it is given by the fully relativistic Friedmann equations. See Appendix C. The first relation in 1.10 is just standard dilution of non-relativistic matter when the volume expands by a factor of r to the power of 3. The second relation is the Hubble law for the velocity field of the homogeneous background, with respect to which the perturbations nu1 can be seen as peculiar velocities. The third is solution to the Poisson equation, applying the Gauss theorem to a sphere with radius r centered at the origin and ignoring the infinite amount of outside matter. This logical jump, known as the gene swindle, is justified thanks to the existence of a horizon in the full relativistic treatment. Expanding the equation 1.6 to first order in the perturbations leads, after the tedious but straightforward derivations, to the linear equations. So thank you so much for watching my tutorial video until the end. Today is the 10th date of the August 2026. Time is 9:05. If there is any simulations for some candidate here, for example the Gaussian theorem or some other sort of phenomena here, you can find it from github.com/masterscript, github.com/cautious script, and github.com/saffroscript.